Um, Nika Sokolova will be our next speaker.
Hi everyone, I'm Nika. I'm a PhD student at King's College London, and I would be talking about our work which we are doing with Julius, who is in the audience, who is a postdoctoral researcher. And first of all, I would like to thank organizers for inviting me to speak. Alright, to start, I would like to say what setup we're interested in, and we consider scattering of two BPS operators into some long operator. So we have OP plus 2, O2, 1/2 BPS operator scattering into some long state with some scaling dimensions P and R charge. These operators originate from single trace operators. We would like to call such operators stringy operators, and we expect them to grow at strong coupling as follows. So the leading coefficient is parameterized by the string mass level, and essentially we consider the strong coupling of n equals 4 super news in the planar limit. And what we know about these long operators which are exchanged is that they are in principle accessible by integrability. So, and we would like to understand if knowing such operators from integrability can help us in a way understand a bit more of the structure constants, which I plotted here. But what the problem here is that we expect degeneracies at some higher mass levels. And we would like to understand, to track scattering into a particular state, sort of unmixing the degeneracies. But number of degeneracies can be computed, and it was done by this Oxford group. And so here, usually we arrange the spectrum by the rigid trajectories. So we have the leading rigid trajectory, which has degeneracy 1, and then we have subleading and sub-subleading trajectory, and so on. And then degeneracy will grow. And so here I presented the table with degeneracies which we expect for states with 0 R charge. And so the first non-trivial state is small delta equal to 2, L equal to 0. So here we have two degenerate states. And furthermore, we expect them to be at strong coupling, 2 KK towers, with the SO5 R charge which corresponds to S5, spin which correspond to ADS5. And then, in principle, these 2 KK towers should map to some infinite set of states of the field theory. So this is an equals 4 spectrum, a strong coupling. And so we would like to understand what's going on with the towers which we expect from the counting. And what we did, we can find the spectrum of such single trace operators from integrability by using quantum spectral curve. And this is, we did it in the work last year with Nikolai and Arpad. So here I presented you the numerical spectrum of single trace operators. So we track them from weak coupling to strong, and weak coupling data can be obtained, and then numerically you continue the spectrum to strong coupling. Okay, so in principle numerically we have the spectrum, and what do we see? The first obvious observation that we saw that yes, indeed the spectrum form bands with slopes corresponding to string mass levels. Okay, so there is a correspondence, and then also we see that it kind of matches that in every band we have some state, some infinitely many states. And then also because we have this numerical data, we can leave the degeneracies. So we have states with the same quantum numbers, and then we just fit the next terms in the expansion, and then we kind of can distinguish them in a way. So the first term is parameterized by the string mass level. Then the second term, we found that it is just -2. so there is no distinguishing. And then the next term is some coefficient which we fit it as a rational number, and then this rational number, it distinguishes for us the states. And okay, so we would like to make some kind of matching of the KK towers which are expected in our date. And we saw that yes, we can assign our states to consequent towers, and we do it by measuring the Casimir, quadratic Casimir, and we measure the subleading coefficient of it. And then we kind of saw the pattern that states with the same value of J1, which is this subleading Casimir, they can be assigned to the same consequent tower. And this coefficient J1, it distinguishes two degenerated KK towers. So the first green line, we see two states which I was talking about. So these are delta equal to 2 and 0 spin, and we see that J1s are 2 and 14. So okay, so we have these two different towers, and we now can distinguish them. Okay, so now we consider kind of a scattering of 2 BPS state into a long one, and there is a program which is going on a couple of years. This is about computing curvature corrections to string amplitudes, and for example to Virasoro-Shapiro amplitude, and then Tobias, I think, will have a talk this week about that. So basically you can compute some corrections to the amplitude. So this is like 4 BPS correlator of 4 BPS operators, and then you have some exchange operators in the middle, and then you introduce some prefactor and the ansatz for the OP coefficients, and the leading order of the OP coefficient, which we call F0, kind of corresponds to the flat space limit. And then, as a byproduct of their computations, they have kind of a constraints on the CFT data of a very simple form. So they are just some averages over the degeneracies of the states which are exchanged. And so up to their order, they found like that we can find constraints on average F0, average F0 D1, and also the next one, F0 D1 squared. And then what we do, we would like to use our data for J1s to extract some OP coefficients. And then we also noticed that if we use J1, then the average formulas, they are kind of P independent. So then if we run mixed data, we just get the leading OP coefficient for like the whole tower. And then also, so we use this number of constraints which we have in our data, and we get some results for the OP coefficient. So for these two towers which I was speaking about, the two degenerate towers with delta equal to 2 and 0 spin, we have that one OP coefficient is 1 divided by 4, and the second OP coefficient is 0 at the leading order. Okay. So, and then we studied the first 3 mass levels, so delta equal to 1, 2, and 3. So we studied states in this pink triangle, which are the towers which we could access by integrability, because of course then to access more states it's really a lot of time for us to do. And okay, so we have access to the states in the pink triangle, and know what are KK towers which are in the table. Corresponding, and then from our data we know what are the numbers, and then we do our own mixing, and then we see the following patterns, that there are many zeros at the leading order of structure constants. So it means that right. So then, and the remaining numbers are also very simple, and then basically. And then it opens for us some number of puzzles, and then so that we see that kind of one process is subleading to another strong coupling. However, we don't see it at weak coupling, so there is some surprising selection rule which is going on. And so first of all, what is the difference between these two states? Maybe there is some hidden quantum numbers. And then we're thinking that maybe there is some selection rule because of the 10D symmetry in flat space, and would be nice to formulate such a symmetry. Okay, so then, because there is 5 minutes, I will just briefly mention our future ideas and the work which is upcoming. And what we're going to do, we're going to connect states to the Reggie trajectories, such that it can give us more information about the spectrum, especially because if we assign state, if we define a trajectory, we kind of can track all infinitely many states with large delta as well. And so we can do it by the quantum spectral curve. There are known procedures to do it, and then which were done for the leading trajectory, and then we exercise at the subleading trajectory, and they can find like the subleading Casimir. And then we would like to bootstrap basically the leading opaque coefficients for the whole trajectories. This is our goal, and for that actually we found that it's very powerful to use like the large delta limit and to see positivity condition in this large delta limit, because if we impose non-negativity of F0, we can actually restrict some of the coefficients. And then we also impose some other conditions, like the vanishing peak coefficients at the states which at the trajectory which starts not at the first level. And then we do some other intuition like small delta limit, and then also we have some integrability data to check whatever we get as a sanity check. And our preliminary result which we got is the following. So we have that the second opaque coefficient F2, it is vanishing for the whole trajectory. And yeah, so then we can, knowing this individual F, we can actually have many constraints which potentially can be useful to compute Cauchy corrections. And then whatever procedure we used is kind of very general, so we are thinking maybe it can be applicable to other theory where spectral data is not so clearly known. Okay, so yeah, I guess I would stop here, and thank you for your attention.
What's the physical interpretation of the poles of F0?
Physical interpretation of the poles. But I think that there will be no pole because delta is kind of starts at 2 over here for this trajectory. So I think actually it can be conditioned there that there should be no poles.
Okay, and another question is, why do you impose that F0 is positive?
Yeah, because it corresponds to kind of the square of P coefficient.
So you have the beginning of the spectrum with the caption, weak coupling, the strong coupling, the bands. So why are they half BPS operators here?
No, here they're not half BPS operators, it's the long operators.
Oh, I see. So you excluded the half BPS, it's only the long ones?
Yeah, it's only the long ones. Here on the plot there are only the long ones.
And they're not mixing, because at some point in a sense, non-BPS, they're going to hit the BPS ones, or maybe some operator mixing.
That's the next order, 1 over n. Next order, 1 over n. Planar limit.
Yeah, so here is the planar limit.
Okay, thank you.
But they're just have different quantum numbers.
You can have same quantum number, but they won't mix in this order.
want to say something about your ad hoc assumptions?
Which ad hoc?
You wrote ad hoc assumptions somewhere. It sounded a little bit dangerous. Yeah, there. Point 4.
Yeah, ad hoc assumptions is that we have some set of constraints which we are provided, and then we notice some cancellation at small delta, and then we want to just impose that the same cancellation happens for the similar type of constraints which we consider. Yes.
But you don't understand where it comes from?
The cancellation?
Yeah.
No, we don't understand where it comes from. It's just a pattern which we continue.
Any more questions? Okay, I think we should.
Go ahead. So, yeah.
Do we have more time?
We have 4 minutes more.
We still have more time. Anybody? I think then we should just move on, and you can have a long introduction.
Thank you.
Thank you.